Hello, everyone. My name is Rodrigo. I'm a postdoc at CASI, and I'm also a member of the DESI collaboration. And today I want to briefly present the results based on these two papers that we put out on the archive recently, where we reconstruct the dark energy phenomenology using DESI data. So I guess that everyone is familiar with these exciting DESI results, where we see a 2.5 to 3.9 deviation from a cosmological constant. So the motivation behind this work is to ask ourselves whether we need to go beyond W0 WA and whether the data suggests more complicated dynamics in dark energy that cannot be captured by this usual parametrization. So here we want to have a data-driven approach where we don't assume much about the dark energy. And then from this, we can build phenomenological descriptions. And then, of course, the idea is to have an underlying theory that describes this phenomenology. So here we want to give maximal freedom, as I said, to make sure that these results are not driven by this W0 WA parametrization. And the way we do this is that we expand the equation of state using Chebyshev polynomials. So the Chebyshev polynomials have the advantage of forming an orthogonal basis that span the space of continuous functions. So in principle, in the large n limit, one can use these polynomials to model any given function of redshift. So in practice, of course, we don't have infinite terms. We limit ourselves to n equals 3 expansion. And I will come back to this and justify the choice of n. So we can relate the equation of state of dark energy to its energy density evolution, this FDE. And we can look at the constraints coming from BAO here on the left in gray, BAO plus supernova in yellow, and BAO plus supernova and CMB observations by Planck. So first of all, you see that the overall behavior is similar across all data sets. And in particular, we see that the equation of state of dark energy is phantom in the past. And in the low redshift part, we see that it's in the quintessence regime where W is larger than -1. And this corresponds to very negligible energy density in the past. And because the equation of state is phantom, that means that the energy density increases with the expansion. And once we cross the phantom line, then the energy density starts decreasing again with the expansion. And if we look at the corresponding expansion histories, you see that this leads into a bump in the energy density, in the expansion rate of the universe with respect to lambda CDM. And we see a deviation, more than 2 sigma deviation from a lambda CDM expansion history. And one interesting diagnostic that we can look at is this panel here, ohm. So this quantity is basically defined in such a way that if dark energy is not a cosmological constant, then this reconstructed ohm of Z will not be a constant line, but will rather evolve with redshift. So this is quite powerful. And we see that in all these reconstructions, we do see some form of evolution in ohm of Z. Another interesting thing to look at is the deceleration parameter, which is the logarithmic derivative of the Hubble rate. And you see that in the matter-dominated regime, we are Q equals to -1/2. And then, so that means that the universe decelerates. And then when dark energy starts kicking in, then we have Q, which becomes negative. So we have accelerated expansion. And one interesting thing to look at is that all these constraints actually tend to give a rise in Q towards higher values. And in fact, Q equals to 0, meaning that the universe does not accelerate today, is still consistent within 2 sigma from the combined data. Alternatively, one can model instead the dark energy evolution directly. And this is mainly motivated by the fact that in modified theories of gravity, the effective energy density of dark energy can become negative, and this causes the equation of state to diverge. And so we want to cover a larger class of models and make sure that this modeling is not simply limited by an equation of state. So here I'm showing the reconstructions for various supernova compilations, and you see that the overall trends that I was describing in the previous slide remain, mainly that we have no presence of dark energy in the past, and we have a increasing energy density as a function of decreasing energy density as a function of redshift. And again, we see that we have more than 2 sigma deviations in the expansion rate of the universe with respect to lambda CDM. And this trend of a rise in ohm and a rise in Q is also present when we model the energy density. And now if we compare these results with the standard results, W0 WA presented in the main cosmology paper, we see that the overall trend remains. So for instance, we see that the energy density of dark energy is negligible at redshift 2, 3. And then we have a bump at redshift 0.3 or 0.2. And again, you see that this trend in ohm of Z is also present, and we see a more than 2 sigma deviation. And similarly, we see this trend I was describing, Q rising towards 0, and a universe that doesn't accelerate to date seems to be still consistent with the combined data. And the reason why these results are so similar is nicely represented in this figure. When we look at the improvement in fit, the delta chi squared, as a function of the number of free parameters that we introduce in the expansion, you see that at 2 parameters already, W of Z achieves a very similar performance as the W0 WA. FDE requires 1 more degree of freedom to achieve similar performance. But then as you increase the number of free parameters in the expansion, you don't improve the fit significantly. Or in other words, the chi-squared saturates already at W0 WA, and the data doesn't seem to prefer more complex dynamics than what is already captured by W0 WA. And one nice byproduct of this analysis is that we can get constraints on H0 RD and omega matter, independent of any pre-recombination physics. So you see here that the constraints from a modeling of FDE and a modeling of W are quite consistent with each other, and also consistent with W0 WA. And they all seem to prefer lower H0 RD values than the one we infer when we assume lambda CDM. And similarly, we see that the data seems to prefer higher matter densities with respect to what we infer in lambda CDM. So this is, of course, dependent on the supernova compilation. So here I'm showing the effect of changing the supernova compilations. And as you see that as I change the supernova, I move in this degeneracy direction. And another thing that we can look at is see whether replacing DESI measurements by SDSS has a significant impact. And the answer is yes, there is a slight shift, but the results seem to be quite stable and not dependent on this choice of BAO measurements. So now let me move on to the second part of this talk, where we describe more the phenomenology of classes of dark energy models that are coming from more fundamental inspiration. So this work is led by Kushal, who is a grad student in our group in CASI. And so here we basically took inspiration from this work where these authors in this paper were able to show that when you look at different quintessence potential or different dark energy models, in phase space, these lie in 2 distinct regions. So here W prime is a derivative of law W as a function of the number of E-folds. And you see that here there is 2 regions. One is where the models go into this freezing region that asymptotically approaches a de Sitter state, a cosmological constant. And we have this other region that thaws away from -1. So for example, this supergravity model or brain world models that are into the freezing thing. And we have other models like the linear potential or 5 to the 4 potentials that freeze away from -1. And so interestingly, one can map these two regions in this W0 WA parameter space. And you see that again, there are two distinct regions. So the freezing region lies above in this plane, and the thawing region lies below. And interestingly, the upper part of this plane is actually disfavored by the data. The data seems to favor a negative WA. So we are actually going to focus on the thawing type of models. And you see that all these different potentials lies within a very narrow range of values. So we can linearly relate WA with W naught. And this is what we did. So this is, again, this was calibrated in this paper. One can write WA as a function of W0. So this is a one parameter extension to lambda CDM. And I'm showing here the constraints for various data combinations. And so this class of models is representative of pseudo-Nambu-Goldstone bosons or axion-like potentials, where we have basically the field, which is frozen by Hubble friction. So it behaves essentially like a cosmological constant. So you see that in the past, when the Hubble rate is large, we are effectively freezing the scalar field. And then as the mass of the scalar becomes comparable to the Hubble rate, then we start seeing dynamics in dark energy. So it starts thawing away from a -1 equation of state. The second class of models that we looked at is this type of emergent dark energy, where dark energy has no presence in the past and suddenly starts behaving like dark energy and accelerating the universe. So this is motivated by our previous reconstructions that I was showing before. So we looked at this generalized emergent dark energy model, which is described in this paper, which basically has one free parameter delta, which controls the steepness of the transitions. And again, this can have physics-inspired models coming from phase transitions or critical phenomena where basically dark energy is emergent. And the third class of models that we looked at is this mirage class, where again, one can linearly relate WA with W naught. So again, one free parameter. And in this type of models, as the name suggests, the apparent equation of state is constant and equal to -1, despite there being dynamics. And such models are tailored to match the Hubble and distances to the CMB. And so you see that interestingly here, the constraints we get from the various data sets are actually quite similar to the reconstructions we observed in the Chebyshev expansions. And this will become important in the next slide. So here I'm showing the improvement in fit for various data set combinations. So here the blue lines corresponds to thawing models. The yellow corresponds to emergent models, and the purple ones corresponds to mirage type of models. And you see, first of all, that all of these leads to improvement in fit with respect to lambda CDM. But in particular, the mirage class performs quite well and performs as good as W0 WA while having one less degree of freedom and one more degree of freedom with respect to lambda CDM. So when we compute the Bayes factor or the Bayesian evidence, we find that actually for PantheonPlus, we get a 2.8 Bayes factor compared to 0.65 in W0 WA. For Union3, we get a Bayes factor of 4.2 compared to 2.4 in W0 WA. And for DES, we get a Bayes factor of 6.4 compared to 2.8 in W0 WA. So this is actually strong Bayesian evidence in favor of mirage. So mirage outperforms all the rest. And this is according to Jeffrey scales, of course. So to summarize, the DESI results provide tantalizing hits of an evolving dark energy component. And we reconstructed the dark energy properties using a much more flexible parametrization, namely a Chebyshev expansion of Wn energy density, and we were able to confirm the W0 WA results. In fact, we showed that by including more degrees of freedom, the chi-squared doesn't change significantly. And so this suggests that the data doesn't need more complex dynamics. And then in the follow-up paper, we investigated 3 different classes of dark energy models, all of them having 1 single degree of freedom. We looked at knowing quintessence-like behaviors. We looked at emergent dark energy models. And we found that while this improves over lambda CDM, improves the fit, it doesn't perform as good as Mirage. In fact, Mirage is strongly favored in terms of Bayesian evidence. We have a Bayes factor twice bigger than the W0 WA. And this suggests that the equation of state having phantom crossing actually helps in having this improvement in fit. So if the data and its analysis holds, this phantom behavior could have profound theoretical implications for dark energy. It could signal dark energy, dark matter interactions, or modified gravity. And thankfully, new data is on the way. So these are extremely exciting times for cosmology. So stay tuned. Thank you very much.